Hello everyone. Now, dear student, in this lecture we are going to see the different type of the structures such as the simple cubic structure, the body centered cubic structure and the face centered cubic structure. And also we are going to see about the atomic radius, the coordination number, the packing fraction and the density of a crystal. Now first we are going to see about these three different type of the structures. In one of the lectures we have seen the different types of the Bravais lattices. Now we have seen the 7 groups, and in that 7 groups in a 3-dimensional structures the 14 distinct types of the lattices are there. So one of the lattice is the cubic lattice, and in that cubic lattice there are the 3 types of the Bravais lattices, or the 3 types of the Bravais structures are there. The first one is the simple cubic, that is AC. Second one is the face centered cubic, that is FCC, and third one is the body centered cubic, that is the BCC. Now in case of that the simple cubic structure, it is simply a unit cell in which the one atom is located at the every corner. So there are the 8 atoms are located at the every corner of this unit cell, and due to that it is known as the simple cubic type of the structure. Now in case of that the body centered unit cell, in this unit cell the one atom is located at the center of the unit cell, and the 8 atoms are at the corner of the unit cell, and due to that the centered atoms in this unit cell, it is known as the body centered unit cell, or that the BCC type of the structure. Third one is that the face centered unit cell. Now in this unit cell, now there are the 6 atoms are located at the 6 spaces of the cube unit cell, and also the 8 atoms are at the 8 corners of the unit cell, and due to these face centered atoms it is known as the face centered type of the unit cell. So in case of that the cubic type of the structure, or in this group there are the 3 types of the Bravais networks, or the Bravais type of the lattices we can see. Now we are going to see about the atomic radius. The atomic radius is defined as half the distance between the 2 nearest neighboring atoms of the same kind, and it is denoted by the R. Now consider here, if we consider the 2 atoms say as A and B, if we connect these 2 atoms, now then the atomic radius of the atom is equal to the A by 2, if the distance between these 2 atoms is equal to the A. The atomic radius can be determined for the simple cubic structure, the face centered cubic structure and the body centered cubic structure. Now in case of that the simple cubic type of the structure. In a simple cubic system, if we consider A is the edge length, which is the distance between the center of the two nearest neighboring atoms. Now suppose the C and D are the two nearest neighboring atoms. From the center of these two atoms, the distance is A, then the atomic radius is equal to be the A divided by the 2. In case of the face-centered cubic system, the neighboring atoms are at the corners and the one atom is at the center of the adjacent face. So the A, B, C, D are the corner atoms, while O is the center atom of the adjacent face. If we consider A is the length, which is the distance between the center of the two nearest neighboring atoms, then in this case here, for the atom A and the O, from this point A to this point, R is the atomic radius for the atom A, and from this point to this point, R is the atomic radius of the atom O. Therefore, the R is equal to be the OA divided by the 2. From the geometry of the figure, if we connect all these corner atoms and the diagonal AC, then we get the triangle ABC. Therefore, from this triangle ABC, we can write the AC square is equal to the AB square plus BC square. If we substitute the value of AC, now then AC is equal to be this R plus R plus R plus R. That means AC it is equal to be the 4R. Now AB is equal to be the A and also the BC is equal to be the A. Therefore, we get the R square it is equal to be the twice A square, and so we get the R is equal to the A divided by twice under root 2. Now here R is the atomic radius for the FCC type of the system. Now then, in case of that the body centered cubic crystal, that is the BCC, now in this system the neighboring atoms are at the corners and the one atom is at the center of the cube. So here the one atom is at the center of this cube. Now then, if we connect all these points, A to the G, A to the C, then from the geometry of this figure, we get the R is equal to be from A to the O, we get OA divided by the 2. That means R is the atomic radius of this atom A and R is the atomic radius of this atom O. So here this is R plus R, that is equal to the 2R. Therefore, R is equal to be the OA divided by the 2. Therefore, from this geometry of this figure, consider the triangle ABC, then we can write the AC square is equal to the AB square plus BC square. Here this is the AB and the BC are equal to the A, so we get AC square is equal to the twice A square. Now here that AG is equal to the R plus R plus R plus R, that is the 4R. Then from the right angle triangle ACG, now consider this right angle triangle. So write the equation, the AG square is equal to be the AC square plus CG square. If we substitute these, the value of the AG, AC and the CG, so we get the R is equal to be root 3 by 4 into the A, and this is the atomic radius for the body centered cubic crystal. So now in this way we can determine the atomic radius for the simple cubic structure for the face centered cubic structure and also the body centered cubic structure. Next one, now we are going to see about the number of the atoms in the unit cell. Once you know about the structure of the BCC, PCC and the FCC, then we can find the total number of the atoms per unit cell. The total number of the atoms per unit cell is given by using the formula N is equal to the Ni plus Nf divided by the 2 and Nc divided by the 8, where Ni are the number of the body centered atoms, Nc are the number of the corner atoms, and Nf are the number of the face centered atoms. Now here in case of that the simple cubic crystal, how many number of the atoms are there per unit cell? Now in this simple cubic crystal structure, the body centered atoms are 0, the face centered atoms are also 0, and there are only the 8 corner atoms, and therefore you will get the N is equal to the 1. So here the sharing of the atoms in this unit cell is equal to only 1. In case of that the body centered unit cell, now here the body cell, now in case of that the face centered, now here in case of that the face centered, now here the body centered atoms are 0, the 6 atoms are on the 6 faces of the unit cell, so the Nf is equal to the 6, and there are also the 8 corner atoms, therefore you will get the N is equal to the 4. Therefore there are the 4 atoms are there per unit cell in a FCC structure. In case of the BCC structure, there is the 1 atom which is at the body center, so the Ni is equal to the 1. There are no atoms at the face of this unit cell, so the Nf is equal to the 0, and 8 corner atom, so you will get the N is equal to the 2. That means in this case here, so the contribution of the sharing of that the atoms in this body centered unit cell are 2. So remember about that, how we can determine the number of the atoms per unit cell in case of the any type of the structure. Now here we are going to see about the coordination number of the atoms in the unit cell. Then what do you mean by the coordination number? The number of the atoms, ions or the molecules that a central atoms or the ion hold as its nearest neighbor in a crystal. Now that means in any type of that the unit cell, suppose if we consider this is the one of the unit cell. Now then we have seen in case of that how there is the formation of a network of a unit cell. Means suppose if there is the one unit cell, so at its neighbor from all the nearest faces, the another unit cell is also connected with the original unit cell. That means suppose if we consider this is the one of that the unit cell, so along all these faces, suppose if we consider this face, there is also the unit cell. On the upper face, there is also one unit cell. On the lower face, there is also the one unit cell. That means there is the formation of a network or the framework of the unit cell. So it indicates that every atoms get coordinated with the nearest atoms of the nearest unit cell. Then the coordination number is different for the different types of the structures. In case of that, the simple cubic crystal structure, if we consider here the 3 unit cell, if we consider the one of the atom is here, now then it get coordinate with the another atoms such as the number atom 1, atom 2, atom 3, atom 4, atom 5 and atom 6 here. So the atom 1, 2, 3, 4, 5, 6 atoms get coordinated with these atoms, and due to that its coordination number is 6. That means the number of the atoms that a central atom hold as its nearest neighbor. So this is the central atoms. It holds the 6 nearest atoms, and due to that its coordination number is 6 here. In case of that, the body centered cubic structure. Now consider here, this is the body centered structure. The one atom, that is the central atom, is located at the center and the 8 atoms are at the corner. So these central atoms hold as 8 its nearest neighboring atoms in this unit cell, and due to that, that means 8 atoms get coordinated with this central atom, and due to that it having the coordination number is 8. In case of that, the face-centered cubic structure, now like this here, suppose if we consider the 2 unit cell, in this 2 unit cell, if we consider the one of the atoms from the any one face, then we can consider here this atom is the central atoms from this face. Now then it get coordinate with, now see here, the 4 atoms of the upper face. Then which are the 4 atoms? See here, this is the 1. Now here, this is the 2, this is the 3 and this is the 4. Means the 2 corner atoms and the 2 face atoms of the upper side. So here is the 4. The 4 atoms from the middle face here. So it get coordinate with the 4 atoms which are at the 4 faces of this unit cell. So 1, 2, 1, 2, 3, 4. So these 4 atoms coordinate with these central atoms. So that is equal to the 4. And the 4 atoms from the lower face and the lower corner atoms. So these are the 2 atoms from the lower face of this unit cell, and these 1 and 2 are these 2 corner atoms of this unit cell. So that are the 4. In this way, the 4 plus 4 plus 4, that means these central atoms hold the 12 its nearest atoms, and due to that it having the coordination number equal to the 12. So remember that for finding the coordination number, in case of that any crystalline structure, now then first one you have to identify that how many atoms you have to identify, you have to be considered the 1 central atoms and how many atoms hold as its nearest neighbors. Then you will get the coordination number of the corresponding crystal structure. Now here we are going to see the packing fraction. The packing fraction is defined as the ratio of the volume of the atoms occupying the unit cell to the volume of the unit cell. Now that means the packing fraction is equal to be the ratio of the number of the atoms in the unit cell multiplied by the volume of each atom divided by the volume of the unit cell. Now why it is necessary to define the packing fraction? The packing fraction gives us an idea about how closely atoms are packed together in a given crystal system. So the density of the atoms will be increases if the atoms are very closely packed with each other. If the atoms are far apart from each other, now then the density of the atoms will be very low. Similarly, here we can find the packing fraction for all the 3 types of the structure. Now first one is the simple cubic structure. To obtain the packing fraction or to determine the packing fraction, you have to first find the number of the atoms per unit cell of the simple cubic structure. So now here we have already obtained by using the formula, or simply or directly we can obtain that the number of the atoms per unit cell also. Now here are the 8 corner atoms. So at every corner atoms, it sharing in this unit cell is only the 1/8 part. That means here is the 1 atom. So but it sharing in this unit cell is 1/8 part of that atom. Therefore the number of the atoms per unit cell is equal to be the 8 corner atoms multiplied by the 1/8, so you will get the 1. Then volume of the each atom, the volume of the each atom is given by the formula, that is 4/3 pi r cube. If we substitute the value of the r, atomic radius of a simple cubic structure, now then we can obtain the volume of the each atom in a simple cubic structure. If A is the edge of this cube, that is the distance between the 2 atoms, then we can obtain the packing fraction by substituting these 2 values, that gives the 0.52 or the 52%. Now in case of that the body centered cubic crystal structure, the number of the atoms per unit cell is equal to the body centered atom plus the corner atom. So in this case here there is the only one body centered atoms plus the 8 corner atoms, that means here by taking its 1/8 share, so here the 8 multiplied by 1 by 8, so here this is the 1 plus 1, we get the 2 here. And the volume of the each atoms we can obtain it by this formula 4 by 3 pi r cube. The r is the radius of the simple cubic structure, the atomic radius of the BCC structure. By substituting these values, so we get the packing fraction, that is equal to the 0.68 or the 68%. Now in case of the face centered cubic structure, the number of the atoms per unit cell is equal to the face centered atoms plus corner atoms. There are the 6 face centered atoms, and taking the 1/8 share of the corner atom, so you will get here the 3 plus 1, that is equal to the 4. So there are the 4 atoms per unit cell in the FCC structure. By using the radius of a FCC structure, that is A divided by the twice into the root 2, and substituting these two values in this expression, we get the packing fraction, and that is equal to the 0.74 or is equal to the 74%. Now that means here the simple cubic structure having the packing fraction 52%, the BCC structure having the packing fraction 68%, and the FCC structure having the packing fraction 74%. It indicates that in the FCC structure, the number of atoms per unit cell are also large, and due to that, if we consider the whole structure, then the number of the atoms in every unit cell will be increases the total number of the atoms in the crystal structure, and so the density is very high. So all these atoms are very closely packed with each other, and hence the density of such a type of that FCC structure is, or the material those having the FCC structure having the high density as compared to the material those having the simple cubic structure or the BCC type of the structure. Now lastly, in this lecture we are going to see the density of the crystal structure. Okay, the density of the unit cell is given as the ratio of the mass and the volume of the unit cell. So the I is equal to mass of the unit cell divided by the volume of the unit cell. The mass of the unit cell is equal to be the number of the atoms in the unit cell multiplied by the mass of each atom in the unit cell. Therefore the mass of each atom, now we can obtain it equal to the A divided by the N0. Now here the A is the atomic mass and N0 are the Avogadro's number. Therefore the mass of the unit cell is equal to the N into the N multiplied by A divided by the N0. So the density of the any crystal structure can be expressed in terms of the I is equal to be the N into the A divided by the N0 divided by the A cube, where N is the number of the atoms in the unit cell and A is the edge length of that cube. Now in this way we can determine the density. By using this formula we can determine the density of the any type of that the crystal structure. So dear students, now in this lecture It is very important to, to understand about the atomic radius, the coordination number, packing fraction and the density of the crystal. Now these are the very basic things required for the solid state physics. Thank you to all of you.